Welcome back, everybody. Today we're going to finally, after all this time, finish proving R equals T in the general case. We have got almost all the results we could ever want in that direction, minus a few gaps that we'll talk about at the end of the proof, but we are set to finish the proof of R equals T in the general case, assuming the proof of R equals T in the minimal case. So let's spend some time recalling some setup. See video 11.2 to recall the notation and setup involved in this video in more detail. We're going to fix a continuous representation, rho bar, from the Galois group of Q to GL2 of K, where K is a finite field of characteristic sum prime L. We're going to assume that L is an odd prime, that rho bar is irreducible, that the restriction of rho bar to the local Galois group at L is flat or ordinary, that rho bar has cyclotomic determinant, and that rho bar has square-free conductor. Okay. For such a representation rho bar, we'll define sigma sub rho bar to be the set of primes P, such that either P is L and rho bar sub G sub L is good and ordinary, or P isn't L and rho bar is unramified at P. Remember always, at L, the correct analog of unramified is flatness, which is good plus ordinary. Okay? Theorem, R equals T, for every finite set of primes sigma in sigma sub rho bar, the surjective ring homomorphism, which we called phi sub sigma from R sub sigma to T sub sigma, this being the universal type sigma deformation ring, this being the universal type sigma Hecke algebra, this is an isomorphism of complete intersection rings. We have to prove this, okay? We are now set up to prove the general case of that theorem, which is where sigma isn't the empty set, assuming the so-called minimal case where sigma is the empty set. So let's get started, and let's begin by recalling the key results needed throughout this chapter. First, proposition 2 from video 11.6. Please go revisit that video if you need to recall any more detail. Proposition 2 said, keep all the above notation, then there exists a categorically, meaning diagrammatically, universal lifting rho u sub sigma from GQ to GL2 of R sub sigma of the given representation rho bar of type sigma. Moreover, if K prime over K is finite and R prime sub sigma is the corresponding universal deformation ring associated to this field, then R prime sub sigma is nothing but R sub sigma tensored up to O prime from O, okay? Where O and O prime are my rings of integers. And rho u sigma prime is nothing but rho u sigma tensored by 1. 2, and more importantly, R sigma can be topologically generated as an O algebra by dim K H1 sigma Q add 0 rho bar elements. So we had a whole video on type sigma cohomology. Please go see that. That's in this chapter. And then 3, which is the one that we're going to use the most here. If phi from R sigma surjecting onto O is an O algebra homomorphism, if rho is phi compose rho sub sigma, and if WP is the kernel of phi, then homomorphisms from WP mod WP squared to K mod O, those are isomorphic to the cohomology group H1 sigma Q at 0 rho tensored up to K mod O. Okay? So let's also recall the commutative triangle setup and some other notation. For this, O will be a complete Noetherian local ring with maximal ideal M sub O and residue field K. Suppose we are given a commutative triangle of surjective homomorphisms of complete Noetherian local O algebras as follows. So we'll have one map phi from R to T. We'll have another map pi sub R from R to O. We'll have another map pi sub T from T to O, and everything is a surjective homomorphism of complete local O algebras. We also assume T is finite flat as an O algebra. In our case, O is a discrete valuation ring. R is, of course, our universal type sigma deformation ring. T is kind of our universal type sigma Hecke algebra. And pi sub T is the homomorphism associated to a certain eigenform F, as discussed throughout this chapter. We also recall the notation, let I sub R equal the kernel of this map pi sub R, let I sub T be the kernel of this map pi sub T, and recall that the congruence ideal of T, which we called eta sub T, is pi sub T of the annihilator of I sub T. So you're annihilating the kernel and taking the image. Okay? Let's also recall a little bit more setup. See video 11.9 for this part. Let sigma prime be a set of primes between sigma and sigma sub rho bar, and denote by pi sub sigma prime the composition T sub sigma prime to T sub sigma to O. And we'll let eta sub sigma prime, so like the sigma prime congruence ideal, that'll be pi sub sigma prime of the annihilator of the kernel of pi sub sigma prime. Okay? And we'll let WP sub sigma prime denote the kernel of pi sub sigma prime compose phi sub sigma prime. Draw it all out if you have to. Okay? what does proposition 2 tell me? It tells me in this instance with this notation, part 3 of proposition 2, it tells me that the cardinality of WP sigma prime mod WP sigma prime squared is nothing but the cardinality of H1 sub sigma prime of Q add 0 rho sub F tensored up to K mod O, where F is the new form I just got done talking about a second ago. Okay, so we have this. Okay, we're also going to have to recall something from chapter 10, which was one of our criteria for isomorphisms of complete intersection rings that we called criterion 1 back in that chapter. Here's what it says. Keep all the above notation. Suppose O is a complete discrete valuation ring, and that the congruence ideal eta sub t, as per the above notation, is not trivial. Then the O length of IR mod IR squared is always bigger than or equal to the O length of O mod eta sub t, and equality holds if and only if phi from above is an isomorphism of complete intersection rings over O. So basically, we always have this, and if we want phi to be an isomorphism, we have to show the other inequality. Okay? Let's resume the proof. Assume that phi sub empty set is an isomorphism of complete intersection rings. In other words, assume R equals T in the minimal case. We're going to show R equals T in the general case. By proposition 2, part 3, which tells us a strong relationship essentially between cotangent spaces and cohomology groups of type sigma, if you apply that to the case where WP is WP sub empty set, and you also apply criterion 1 applied to the case where eta sub t from that criteria is eta sub empty set, and I sub r from that criteria is WP sub empty set, you get the following. You get that the cardinality of H1 sub empty set of Q add 0 rho F tensored up to K mod O is the same as the cardinality of O mod eta sub empty set. Just write it down. There's no tricks. There's nothing enlightening here. This just is true. Okay? So we have this. Keep this in mind. Okay? Let's also recall the following corollary of propositions 3 and 4 from video 11.9 that we called corollary CC. And that says, keep all the above notation, and then the following is true. The cardinality of H1 sigma prime Q add 0 rho F tensored up to K mod O divided by the cardinality of just H1 sigma Q add 0 rho F tensored up to K mod O. That ratio is always less than or equal to the ratio, the cardinality of eta sub sigma divided by eta sub sigma prime. So the sigma and the sigma prime kind of switch on this side. Okay, so we're going to need this. If you combine this with this equality that we just discovered, you get the following. So combine that result we just discovered with corollary CC in the case that sigma is the empty set and sigma prime is some given sigma and sigma rho bar. You immediately get the following. You get that the cardinality of H1 sigma Q add 0 rho F tensored up to K mod O is less than or equal to the cardinality of O mod eta sub sigma. Again, just write it out and you'll have it. Okay? And then a second application of criterion 1 applied to the case where I sub r is WP sigma and eta sub t is eta sub sigma, combined with proposition 2, part 3, that isomorphism between cotangent spaces and type sigma cohomology groups, applied to the case where WP from that proposition is WP sub sigma, concludes the result, because what we've essentially shown is the other inequality up in criterion 1 here. And by criterion 1, that means the associated map we're after, phi sub sigma, is an isomorphism of complete intersection rings. And there you go, my friends. We have finally proven after all this time R equals T in the general case, assuming the minimal case. Let's take a second and see if there are any holes or gaps still in the proof. There are a couple. First, we need to study the flat deformation functor to make sure that the R sub sigma from video 11.2 actually exists. Like, do we actually have universal type sigma deformation rings? We don't really need to do very much left to finish that, but there's some stuff with flatness that we have to work out. Okay. In other words, is being of type sigma actually a deformation condition in the sense of Mazur from chapter 8? This will be discussed soon in a later chapter, I think 2 chapters from now, by appealing to and studying Ramakrishna's thesis. Okay. Finally, we still need to prove part 3 of what we called key theorem 3 in video 11.4. And the reason we didn't do it in this chapter is because it turns out it's best to do it at the same time that we study Ramakrishna's work and the flat deformation problem. So we'll do these at the same time in 2 chapters. So what are we going to do next? Immediately, what's the next chapter? We're going to start the beginning of the proof of R equals T in the minimal case, which is the case where sigma is the empty set. So thanks for watching. We've reached a milestone here. I'll see you all then, and thanks for watching.